All right, everyone, let's settle down, please. Um, so I guess before we begin for today, since we are in the last couple of weeks, really, we do have our homework 9 part 2 due today, and then I'll assign a last homework also tonight, and um, most likely I'll make it due part 1 next Monday. Um, and then part 2 would be on Wednesday. There, of course, won't be a homework due in the last week. We do have our final exam schedule. First day, first exam, I think Monday, 8 a.m. And I think, so this week, what I plan to do is to finish off this topic of stiffness method. Um, and everything that we finish off until this week would be on the final exam. Nothing from the last week would be on the final exam. But still, just to make sure you have sufficient motivation to attend the last week, what the plan right now is that for Dr. Liu to do sort of a review or maybe some sort of an overview of standard structural analysis software like SAP. I'm not sure how many. Has anybody here used SAP before? A few of you. Okay. So that would be sort of a quick tutorial on SAP and possibly things that you should watch out for while modeling. It's very easy, as you all can see, using your computer programs. It's very easy to trust the results that you get out of the computer programs. But the results that you get out of the computer programs completely depend upon the input file or quote unquote the model that you send in. If you send in a model that is flawed, the results that you get out from it will of course be wrong. So you have to really watch out for those kinds of errors with computer methods. So last week would be devoted to that, and there would be a sample final exam that I'll post, and Dr. Liu might discuss that also on Friday. Any questions, Drew?
Is this final cumulative or not?
Say it again?
Is this final cumulative?
Yes, the final will be cumulative. Everything that we've covered in the course will be on the can be on the final exam. I think a total of 5 or 6 questions. I don't remember exactly how the format has been in the past, but I'll post a sample exam very similar to your quizzes, just twice the length. Miles?
Are we allowed to use the crib sheets that we made previously?
Yes, you are allowed to use the crib sheets you made previously. So there's 4 quizzes. That means you can have up to 4 double-sided crib sheets for the final exam. And I'll send out an announcement for that. Any other administrative questions? Okay. So let's jump into the stiffness method. What I'll do is I'll very quickly review what we did last time, and then we'll finish off this method, stiffness method for frame problems that I had told you that I talked about. Quick word of advice again. Stiffness method, the way it is covered in your books, is a fair bit different from the way I'm doing it. The codes that I've given you are based entirely on my notes. I think if you should follow one thing. Either my notes, if you try to compare that with the method that the book adopts, there's quite a few differences. Of course, the results would be exactly the same. The global stiffness matrix that you end up with would be exactly the same. But how to build it, I feel that the book takes a little bit of a longer approach than what I've done here. So if you do have questions, make sure you follow the notes, and if needed, of course, go back to the video lectures and let me know if you have any questions. So what we did last time was we tried to finish off, well, we did finish off the stiffness method for beam problems. Let me recall where that was. So as you remember, for the beam problems, we decomposed a structure, a beam type structure, into nodes and elements as usual. We constructed the element stiffness matrix using these 4 modes of deformation. So we came up with this 4 cross 4 relationship that relates the degrees of freedom at the two ends of a beam element, which is basically transverse displacement and rotation at the node. There is no axial displacement for beam problems. We relate those degrees of freedom to the forces and moments at the ends of the beam, and at that point we can go ahead, compute the element stiffness matrices of each of those elements, assemble them in a global stiffness matrix. We ran through this code to see how that's done, and then the code essentially spits out uh, deformed shapes, reactions, shear force and bending moment diagrams, and so on. And one key thing that I think also mentioned here was that when you calculate the shear force and bending moment diagrams using this beam code, you can do that easily by actually first picking out the degrees of freedom that belong to each element. So for example, in this problem, there are two elements. The first 4 degrees of freedom, 1, 2, 3, 4, belong to element A, and 3, 4, 5, 6 belong to element B. So if you pick out those, the first 4 degrees of freedom, maybe I'll mark that here as well. So that's first 4 belongs to element A, which I'm calling UA, and the last 4, these are the degrees of freedom that belong to B. Now, once you have your UA and UB, after everything has been solved, to calculate the shear or to draw the shear force diagrams and bending moment diagrams, we noted that what we needed to do was to take UA and pre-multiply with Ka. So Ka is the element stiffness matrix in the well, local and global coordinates are the same. So Ka for this element is this matrix. Take that Ka matrix, multiply with the UA vector, we get another 4 cross 1, and those are the nodal forces and moments. And well, 2 of those are actually opposite in convention to our shear force and bending moment. So we switch them, and then we draw the shear force and bending moment diagram. So that's something that's important for you to keep in mind, which we'll also need to do for the frame problems, as I'll talk about that in a little bit. We also talked about how to deal with distributed loads. So I told you last time that the way we actually deal with it is to break it up into 2 parts. One part which we solve by hand, where we assume that the particular span that has the distributed load is fixed on both of its on its two ends. And if it is fixed, we can calculate the fixed end moments for this particular structure. So, and as I mentioned, these fixed end moments are on the last page of your textbook. There's a table where the first column in that table shows you. I think maybe I want to talk about this a little bit as well. So let me pull this up. So all right. So this is the table of fixed end moments that I'm talking about. If you have a distributed load on a certain span, then you can assume, first of all, that for at least the hand problem, that that this span is fixed at two ends, and under the action of this uniformly distributed load, what these end moments would be can be calculated using the force method. We know how to do that. But not just for uniformly distributed load like this, you could have other distributions, triangular distribution in different shapes, and in fact, even point loads. So if you have a single point load, the way we have been dealing with a point load in the middle of a span is by actually creating another beam node at this point, right? So if you create a beam node at this point, then you can specify that the vertical load at that point is P, and and the method, of course, works in that way. But an alternate way would be to not create a node here, and what that allows you to do is to have a smaller global stiffness matrix, because you would have lesser number of nodes, lesser number of elements. But in general, you would use these fixed end moments that are given in this table to implement the first half of the problem with distributed loads. And yep, go ahead, Drew.
For the exam, will we be given this table? Or
Yes, if I expect you to use this, then I would of course give it to you. Yeah. So another quick point here. Maybe let me ask you a question actually regarding this. So for this particular problem that we did last time, we had a distributed load here. So we said that we will break this problem up into two parts. One that is to be done by hand, where this span is frozen, and we know what these fixed end moments and fixed end reactions would be from that table. So the moments are WL square over 12 and so on. And then there was an additional 12 kip load at point B. So we said we'll create a node here, and we have this 12. So we had 4 nodes and 3 elements. Is there a way to solve this problem? I think I remember mentioning that there is a way to solve this problem with just 3 nodes. Do you think there's a way to solve this problem with this 3 nodes? So how do you do that if there is a way? Josh?
You have to add the moments and forces on 2 and 4.
Right. So what you're saying is that consider this point load as a special case of a distributed load, which would be up here. I know what the fixed end moments due to that point load would be, and I can calculate and apply those fixed end moments to these points, and then solve the problem as usual using MATLAB, and solve part of the problem with hand by using the hand method that we talked about last time. Another good thing about this tables is that in certain cases, when you have like an end span, where at the end span on one end you have a roller, and of course the other end is continuous, in that case you can use a simpler diagram like this on the right column of this table. In this right column, you can see that the left end is fixed, right end is a roller, which is very similar to the problem that we have here. If there is a right end on a roller, then you need to fix only the left span or the left end of this span and use the fixed end moment at the left. Okay, so what I'll do is I'll continue this example and with this method by using just 3 nodes, and I'll post it on Blackboard for you to take a more detailed look of how you would need to solve problems which have the right end is a roller, and you can use these tables of fixed end moments to solve those problems. Okay. Somebody else had a question here? No? Okay. So let's go back to this example. We break it up into 2 halves. The first one to be done by hand, the second one to be done in MATLAB. We already know how to create these input files. And the solution procedure exactly remains the same. At the end of the solution, when you have the displacements and when you have the reactions and the external forces computed by MATLAB, you essentially have this solution. You have the solution where the applied loads are there in the form of fixed end moments. You have the reactions that MATLAB has computed, and what you want is to add your hand calculation to whatever MATLAB has calculated. And we said last time that using these fixed end moments, you can draw the shear force and bending moment diagrams of the hand calculated part, add it to whatever MATLAB calculated to obtain sort of the global response of the problem. So for problems with distributed loads, there is something that needs to be done by hand. And you just superimpose the solution that you get from MATLAB to your hand calculations, and that's the way you deal with it. And then finally, we started off this method for the stiffness method for frames, where we said that essentially these are all elements that can bend. These are beams in their own local coordinate systems, but when assembled, this forms a frame structure where each node now has 3 degrees of freedom instead of 2 degrees of freedom. So for this structure, for example, we created 5 nodes, and for a general node I, if the degrees of freedom are 3i minus 2, 3i minus 1, and 3i, then for 5 nodes, we immediately have 15 degrees of freedom, right? And what we did last time was to try to come up with the force and moment, force moment, and the displacement rotation relationship for a frame element. We said, first of all, that if I have a frame element in some orientation in space, then we attach the local coordinate system to that orientation exactly the same way that we did for trusses. And in that local coordinate system, we said that the axial behavior of this element is completely decoupled from the bending behavior of this element, which is a good approximation for cases when your deformations are small, right? So you can hopefully visualize that if I extend this beam or the frame element a little bit, and then give it some bending degree or bending displacements and rotations, then the response of the bending would be completely decoupled from the response of the axial element. The axial element responds exactly like it would be a truss, whereas and the bending element, the bending response of the frame element is exactly like it is a beam. And both of those responses are something that we have calculated before, where we said that the axial response is exactly what we had with the truss elements in the local coordinate system, and the bending response was given initially in these 4 sub-blocks of the matrices, which were exactly the beam element stiffness matrices. So all we did last time was to combine them both to try to get a measure of now the 6 degrees of freedom per node, because each node has 3 degrees of freedom, to 4 forces and 2 nodal moments. So this relationship, as I mentioned last time, was something that is equivalent to this relationship for the trusses, or the 4x4 relationship for the beams that we have developed. This is a force displacement relationship for a frame element in its local coordinate system, right? So it doesn't really matter in what orientation the frame element is. This will always be the relationship for a frame element in its local coordinate system. And what does it depend upon? Depends upon area of cross section, Young's modulus, length of the element, I, second moment of area of that beam, and pretty much nothing else. So as long as those 4 quantities are the same for 2 elements, the local element stiffness matrix would be the same. It's only when you take, for example, this element and this element, let me say, assuming that this portal truss or portal frame is symmetric, what would be the element stiffness matrix for this frame element and this frame element? Would they be the same? In the local coordinate system, they'd be the same. But after you transform it to global coordinate systems, they would, of course, be different, right? And this is the other good thing about the stiffness method. Once you sort of get all the steps down, that there's a local stiffness matrix, then you transform it, then you assemble it, then you solve it, the boundary conditions, free and specified degrees of freedom. This procedure works exactly the same for trusses, for beams, for frames, for any structure really. And so a quick word about transformation. Last time, I think we said since there are 3 degrees of freedom, we will have this x prime, y prime as the local coordinates and xy as the global. We said, of course, that the z prime is the same as the global z. So there is no transformation needed for the theta or the rotation degree of freedom at each node. But all the other equations were exactly the same. So you can hopefully see that these 2 equations that relate a vector v, which is a physical quantity, does not depend upon your coordinate choice. This vector v expressed in the xy coordinates versus expressed in the x prime y prime coordinates it's two different descriptions of the same physical quantity. They are given by these two equations, which is exactly the same as what we had. Let's see if I can pull that up here. These two equations that we discussed for the truss problems long back, right? These two equations are exactly the same. We've just added a third, theta I and theta I prime. And what that means is that we'd have to add a row and column to our transformation matrix. This is what I call T-mat in the code. And of course, the inverse relationship is with T transpose. There is a small correction on your handout that I would like you to make. This is not TM. This is just this 3 cross 3 transformation matrix. Similarly here, it's not TM. This entire matrix is what I've been calling TM. So T element, which is equal to TM. TM is the whole thing, which is composed of two 3 cross 3 matrices T, or transformation matrices, which look like this. Okay, and you'll see that in the code also in a little bit. So using this transformation matrix, we'll transform the local element stiffness matrix, which I think I did hurriedly last time. This was the relationship that we had come up with. Qm prime Km prime is equal to Km prime times Dm prime. This is the local force displacement relationship for frame elements. I'm just writing it in a compact way. I'm writing the previous this relationship. Maybe I'll write that here as well. This guy is Q. It's already written. Qm prime. This entire thing, 6 cross 6 matrix, is Km prime in the local coordinate system. And finally, we have this Dm prime also in the local coordinate system. So I'm just writing this 6 cross 6 in a compact form. So I have that here in the compact form. And I'm going to pre-multiply this entire equation on both sides by this transformation matrix T. And this should be Tm. Tm. So this is the transformation matrix for the element. And if I pre-multiply on the left, I have to pre-multiply on the right also. And in the middle, I have this T transpose times Tm. Can anybody tell me what that would be? T transpose times Tm? 1 or identity matrix, right? So yeah, in matrices, 1 is essentially we have an identity matrix of what size? What would be the size of that? 6 cross 6. That would be a 6 cross 6 identity matrix. So of course, identity matrix times dm is equal to dm. So you can verify that this equation is nothing but this equation pre-multiplied with tm. Okay, and that this procedure of pre-multiplying with tm, what that allows us to do is to create the force displacement relationship for a frame element in the global coordinates. So remember, we were in the local coordinates for a frame element in some local coordinates like this. And if I have all frame elements in some local coordinates, I cannot add them. I need to convert all of them to global coordinates before I can add them. So this procedure of this transformation matrix is basically what converts that to global. And once it is in global, I can add them or assemble them as we've already been doing for truss element problems and beam element problems. So here's sort of a quick run through of that code. We are trying to solve this problem. Again, 5 nodes, 4 elements. There's a 20 kilonewton load on the top. Input files, I think you are very well able to read these now. 5 nodes, 4 elements. We are just telling them which node is connected to which other node. This is 2e to the 11, 20 gigapascals is the Young's modulus. Area of cross section is 10 to the minus 2 meters square. Again, you have to be very careful about units. You have to be consistently using the same units in each one of those quantities. And this is 5, 10 to the minus 6 meter to the 4, right? This is the second moment of area or moment of inertia of each one of those beam elements. Boundary conditions, both those nodes are fixed in the x and y. So node 1 is fixed in 1 and 2, node 5 is fixed in 1 and 2, and there's a load of 3. So that's what an input file for frame elements looks like. And I think on your handout, the code structure is also given, which hopefully you can see that it's extremely similar to what we had previously. This is the initialized part for the frame problem where we create global matrices of the right size. Note now that this is 3 times node degrees of freedom, because there are 3 degrees of freedom per node. Earlier it used to be 2 times 3 nodes, 2 times number of nodes. Boundary conditions, nodal loads exactly the same way. Global stiffness matrix, this is of course the most useful or most critical part of the code, where we build K global. Element degrees of freedom is calculated in very similar way, but you have to now keep in mind that there are of course 3 degrees of freedom per node. Solution exactly in the same way, and everything else is just plotting. Here's the K element subroutine. So this guy, frame element 2D, that's the main subroutine that calculates the element stiffness matrix for a frame element. All it needs is the coordinates of the 2 nodes. It needs Young's modulus of that element, area of cross section, and I. That's all it needs. And it gives me back the element stiffness matrix. So how does that work? You hopefully recognize most of this code from the truss element problems. We have E1 and E2. Anybody remember what E1 and E2 were from the truss problems? So let me draw a frame element. I have some frame element, node I, node J, and element M. This is a vector we called n hat. You remember, a vector along the truss direction. And here, E1 is this vector. And E2 is a vector that is perpendicular to this element, which we called m hat. So E2 is this vector, which hopefully you are able to see. E1 is nothing but node 2 x direction, node 2 y direction. So we are just taking a vector pointing from I to j and dividing it by its length. That gives me 2 unit vectors, which happen to be the same, which happen to be the components of the transformation matrix that we need. So we create a T matrix that is in the form of E1 and E2, which is exactly what we had in the truss problems. And now we have added this element T3 cross 3. So maybe what I should do, okay, I'll do that in a minute. We had this C cosine minus sine cosine matrix, which was a 2 cross 2. In MATLAB, if you say Tmat 3 cross 3, which doesn't even exist till now, is equal to 1, what MATLAB does is it extends the size of that matrix, and it creates a 1 here, and whatever elements are not specified, it creates zeros. So this matrix now becomes the transformation matrix for for each degree, for each node. You take T element, which is T mat, zeros of 3, zeros of 3, and T mat. That's the transformation matrix for the entire element. That's a 6 cross 6. Now construction of the element stiffness matrix. So I create it in two parts. One is the K bending part, which is exactly the same as a beam problem. So that's a 4 cross 4 beam K element. And you have K axial. That K axial is AE over L times 1 minus 1 minus 1, 1. So you see that in these two lines, we have created the bending part and the axial part. All I need to do now is to put them in the right locations of that big 6 cross 6 element stiffness matrix, just like the way that we did by hand. And you can see that in K element local coordinates, I'm saying that the 1, 4, 1, 4 rows and columns have the axial components. And that's something that you see it right here. 1, 4, 1, 4. In the 1, 4, 1, 4 rows and columns, we have the components due to the axial stiffness components, and the rest of them, which are 2, 3, 5, 6, 2, 3, 5, 6 rows and columns, we have the bending components. All of the cross degrees of freedom, all of the cross components are 0. And that's exactly what's happening. All right, where is that? That's exactly what's happening in these two lines. First, we assemble the axial part, then we assemble the K bending part, and this right here finally is the Tm times Km prime times Tm transpose is equal to the Km in the global coordinates, which is the same relationship that we had up here, right here. Oh, what's that? Yep, right here. K global is equal to T times Km prime times T transpose. So once we have the global element stiffness matrices, we assemble them. And just for sake of example, again, without running through the code in detail, I'm kind of going to show you. We have this K1, K2, K3, and K4, which, as you can see, element 1 stiffness matrix in the local coordinates, that's what I'm calling K1L. In K1L and K4L, should they be the same? Right? So hopefully you can all match up the numbers between 1 and 4. They are indeed exactly the same. 2 and 3 in the local coordinate systems would be exactly the same. And couple of other things, when we convert these local to global using that T times K prime times T transpose, I get a slightly modified K1 in the global coordinates. What has changed really? What has changed is, if you see this number 0.015, originally it was at location 2, 2. So the local matrix that we had calculated, this local matrix that we had calculated was for an element in its local coordinates, right? If I take those local coordinates now and rotate them by 90 degrees, that all it does is changes some x prime to global y, some global x to y prime. And that's why going from a local stiffness matrix to a global stiffness matrix that goes from kind of horizontal to vertical, all the numbers remain exactly the same. They are just rearranged in the correct columns and rows. And maybe what I'll also do is I'll show you the transformation matrix for this. for which I would have to go into the code. So I'll put a breakpoint on my frame element 2D line. And by the way, of course, this code is also something I'll post shortly. So we run this, choose frame 2, I think. And when I step into this program, I'll come, maybe I'll step through here. So as I was just telling you, this transformation matrix right now for element 1 is just 0, -1, 1, 0. This is the transformation matrix to go from a horizontal to a vertical orientation. Then 3 cross 3, as soon as we execute this line, now the transformation matrix is the exact same, except now the third cross third element is the 1, just like I was telling you. And we create T element transformation matrix. You can hopefully see that the first 3 cross 3 up here and the bottom 3 cross 3 here, they are exactly the same with off diagonals that are 0. And we take this transformation matrix, we construct the K bending part. This is exactly the same as beam bending. We create the axial part, which is those 4 non-zero components of the truss element, and we assemble them into the K element local. So this is the local element stiffness matrix, which is the same as given in your handout. And this one line of T multiplying with transformation matrix before and transformation transpose after. Of course, that's a long calculation that if you had to do by hand, it would take a long time. But the good thing is that this calculation can be very easily done for this particular element because it's oriented vertically. So you do that, and all that it does is it changes the positions of those elements in the required locations. That's how we get K1 and K4. K2 and K3 are, of course, much more complicated because their transformation matrices are completely full. So maybe I'll keep on executing this and I'll show you what that looks like. So again, we'll go in for the second element and continue up to this point. You should be able to see that the transformation matrix for the element 2, which is inclined now, hopefully you can see that cosine, minus sine, sine, cosine. Third 3 cross 3 is always 1, even if the element is inclined. So this 3 cross 3 bottom here, that 3 cross 3 on the top left there are the exact same. And now if you have to do this transformation matrix times this K local times this transformation transpose, that's a long calculation that I would absolutely not expect you to do by hand. But basically that's how these two K2 and K3 were calculated. Assembly, you get a big huge 15 cross 15 matrix where how many degrees of freedom are free and how many are fixed for this particular problem? This is a pin and a pin. So out of the 15 degrees of freedom, how many are free, how many are fixed? Say that again. That's right. 11 free because, and indeed 4 fixed because 2 degrees of freedom, X and Y displacements are fixed here. The rotation is indeed free. So that means that ultimately we'd be solving an 11 cross 11 system of equations, which of course MATLAB solves it for us in no time. And if I let the code run out, it plots all these responses for our system, and let me pull those up one by one. Figure 1 is the reactions and the deformed shape as usual for the same way that we had for the beam problems. Figure 2, this is something new from the beam problems. This is the axial force diagram. And of course, for frame problems, in addition to bending, you can have axial forces also. Axial forces change between members, right? So how do we calculate axial forces? Maybe let me ask you this. How would you calculate axial forces if you knew that this was the response from MATLAB, which MATLAB has already given to you here? MATLAB tells me that these are the displacements at the 15 degrees of freedom. Some of those were 0, as we knew. And these are the reactions and the loads at those degrees of freedom. So if I know these degrees of freedom, these global degrees of freedom, and I want to plot the axial force diagram, how would I do that? Thoughts? Andrew? Multiply what by AE over L? Deflections at what points? For the axial components, that's right. But for this problem, for frame problems, getting the axial components is a little bit different from the beam problems. You remember what we did for the truss problems when you had to calculate internal forces for the truss problems? How did we do that? How did we calculate internal forces for the truss problems? Yes, we do have to convert it to the element coordinates, and that's the transformation we need to find the axial components. So let me show you, maybe remind you first what we did for the truss parts, and then oops. Support. Huh, that's strange. Right. So you remember this problem for the trusses when we were dealing with it? This was an indeterminate truss with actually no external loads applied, but we said that member 2 was short, right? And we said we wanted to find the force in member 2 after computing everything. So we first extended member 2 to the correct length, and to do that we needed to apply these external forces 9600 and 12,800 at the two ends of this member, and then we allow MATLAB to solve for it. MATLAB gives me these displacements and forces at all the degrees of freedom. I pick out the displacement degrees of freedom for element 2. I convert this element 2 displacement degrees of element 2 into the local coordinate system, and then I multiply it with, I've not shown the details of that calculation here, but okay, so that's something that I need to do here. Is the transformation, right? Example here. Right, so so after MATLAB has computed these displacements and force degrees of freedom for me, the element degrees of freedom corresponding to element 1 would be what? What would be the element degrees of freedom corresponding to element 1, which is connected to node 1 and node 2? The 1 through 6. First 6 degrees of freedom would be for element 1. So let's see if I'm counting correctly here. Nope. So the first 6 degrees of freedom out here, they belong to element 1. So I call them U1. And can I just directly take this U1 and multiply with or pre-multiply with this K1 local? I can't. I need to convert this U1 to local coordinates. How do I do that? How would you convert to local coordinates? Pre-multiply with UT transpose, right? So you see when we set transformation to go from a local coordinates to global coordinates, we pre-multiply with T. So if you want to go the other way around, if you want to go Q, or maybe I should write with D because I'm talking about UM. This is the global displacement degrees of freedom. I'll pre-multiply with T transpose to get the local UM prime. As soon as I have local UM prime, so I'll go back and write that here. U1 prime is equal to T M transpose times global U1 that we get from MATLAB. Now take that local degrees of freedom and now compute local forces and moments equal to Km prime times Um, or yeah, local degrees of freedom would be Qm prime equal to local element stiffness matrix times the local degrees of freedom. Once you have the local coordinates, then plotting these axial force and shear force and bending moment diagrams goes exactly the same way that we did for the beam problems, right? The local, and maybe I think this is another thing that I need to point out here. In the local coordinates, once you've found out these Qm primes, would Qij be the axial force positive or negative? And maybe I need to show you the diagram for this. So Qij is pointing in this direction, right? If I have an element oriented in some random direction, Qij is pointing towards the right in the positive x prime direction. Qj prime is also pointing to the right. Is Qj prime a positive axial force or Qi prime? Qi prime would cause compression, Qj prime would cause tension, right? I have a frame element in this direction. At node I, it is pointing in the positive x direction, which is causing compression, which would be a negative axial force. So if you, when you're drawing the axial force diagrams for that, you would have to take negative here. And just as we did for the beam problems, you would have to take negative for the bending moment here, negative for the shear force here, and that negative axial force, maybe I'll write that as well, negative axial force, negative bending moment, and negative shear force. When you add, when you take those three negative components, you can plot the axial force diagram, the shear force diagrams, and the bending moment diagrams for each one of those elements. So anyway, let me stop here, and I think this might need some more clarification, which I'll do next time. And I guess I'll post a homework 10 also tonight, which would require some of these beam and frame problems. So see you all on Wednesday.
stuff in